is smaller. All right, good. All right. Okay, so let me start. And first, let me say thank you for Nakai Sensei and the other people who invited me for the seminar and prepare everything for today. So my name is Diego Thomas. I'm now associate professor in the Kyushu University, and I'm working on the topic of, so basically I come from the domain of computer vision, and more precisely in the domain of 3D vision. So how to see, how to make 3D maps of the world, as we make content from videos and images. And so today I prepared like something like 40 slides, maybe to talk something like 45 to 1 hour. And I'm very happy if you have some comments in the middle to discuss. So if you want more precision or you have some comments, don't hesitate to interrupt me while I'm talking. And so today, the title of my presentation is creating bridges between the digital and the physical realms with using 3D vision. Right. And at Kyushu University, I'm now part of the computer vision and graphics labs, and I'm now working on the digital humans, basically. All right, so maybe at first, let me very quickly introduce myself. So I come from France, from an engineering school, which is called NCMAG, which is a school specialized in applied informatics and applied mathematics and informatics in the Grenoble. Maybe you know about the city, Grenoble. It's kind of the French Silicon Valley. So you have many startups. And yeah, and if you have some applications of students from France, from NCMAG, yes, normally they're good students. And so at the end of my master in France, in all the masters, all the engineering school, at the end of the master, it is mandatory to do a 6 months internship, basically. So everybody has to do this 6 month internship at the end of the so it's mandatory to make a 6 months internship at the end of the master, and now I think it's even mandatory during the master to spend at least one time a few months out of France, so to go, right? And in my case, I decided to make my internship in Tokyo at the National Institute of Informatics. And it was the first time I was going to be an engineer, but I really enjoyed my time doing some academic research. And so I decided to stay in Japan and as a PhD student with Professor Sugimoto at NII. And then I did my PhD from 2009 to 2012. And after my PhD, I stayed 3 more years at NII there is like actually French Laboratory of Informatics in Tokyo. So I was in both NII and what is called GFLI there. And after my postdoc, I moved to Kyushu University, first with a GSPS fellowship, and then became assistant professor in 2017. And since recently, since 2023, I'm now associate professor at Kyushu University. All right, so okay, so before I talk about my research, let me start my presentation today with this graph. And this is the only graph of my presentation today. And what I'm showing in this graph is the evolution of the GDP per person in the world since 1820, so something like 200 years. And obviously, what you can see from this graph is very happily for us, we have become super rich, right? Like you see the curve is like becoming very rich. And if we think about it, like, I mean, compared to 200 years ago, now everybody has a car, everybody can move like at 100 kilometers per hour very easily. If I want, I can take my car and go to Tokyo tomorrow. These are kind of things like 200 years ago, even my kings could not even dream of doing, of having this level of life, right? So we become very rich. So why is this? And one answer is that what's changed in the last 100 years, in the last maybe 60 years, is that we have a lot of machines to help us now. So we have a lot of machines that work for us, that bring the food to our home, that make us move super fast. And we use this machine extensively in all our tasks today. And these machines, why? So we are not, we're not so much more smart than people were like 200 years ago. We have people like 200, 300 years ago, or even before this, which were very geniuses. But what changed? Why we could make use of so much machines? One big point, one big reason is energy, right? And what changed is that around the 50s we have become able to extract petrol, right? And now we have a lot of petroleum. This petroleum are being we feed the petrol to the machines, and the machines give us kind of a superpower to become very rich, right? And we get used to this, right? But now I'm talking to you through my computer, which is a machine, and it is made of a lot of product that comes from the petrol, right? All the plastic we have come from the petrol, all the cars and planes are running off petrol, etc. So this is super, it's very interesting for us. But now the question is rising, and I think it's kind of big question is what happened in the future and maybe in the near future when there is no more petrol, right? And then the machine don't have food to run, and when we start to like about energy. And I don't have any solution about it, but one way I think is that at least to move this deadline a bit further, I think what we can see today is, I think one big question for now is how can we make our machines smarter and more efficient to help our societies, right? Now we have many machines, as I say, like the cars, they're good, but they are kind of not very smart, right? Most of the cars, uh, if you close your eyes and just run straight forward, then it will just crash, right? So could we make the machine smarter and the machine smarter so that it can be more efficient in the way it uses its energy and the way it helps our society? I think can be one of the ideas. And for this, I think the machines need to understand better about our world. And so, yeah, so let's see, like the question now is, okay, how smart are the machines today? Okay, so let's see about machines we use every day in our home, for example. So in my home, if I give a 2D map of my home and I give this map to robots, like the Roomba, and maybe you have Roomba in your home, then the robot can move in my room and clean up my room. And now I think you don't have to do anything and it's working very, very well, right? So these things, machines are very good. But now, if we ask the robot to do a very simple task in the 3D space where we live, then just, for example, put a box on the shelf, then still it fails totally, right? It's total fail, and comes from Boston Dynamics, right? So maybe we know the very nice videos of Boston Dynamics robots that do like a flip, that jump everywhere, but maybe you see less often all the fails that the machines do before reaching like nice level, right? So still like robots, when they do like some kind of easy tasks in our 3D world, then they fail, right? So why? One thing is that the robots, to be more precise, to be more successful, what it needs is to have this kind of detailed 3D understanding of our world, which means like it needs to know the geometry, the space around it. It needs to understand what are the objects around it, and the robot also needs to understand how to interact, right? And that can be how to interact with other objects, but that also means how to interact with a human, for example, right? So it seems to me that what is still missing, what is still lacking for the machines to be smart, is a good 3D understanding of our real world. And that's why the machine is still kind of not very smart in the end. And right, so yeah, so today we have 2D maps and 2D maps like Google always make a 2D map of the world. And I think for the future, what we are looking for is how to make 3D maps of the world, right? And if we look at how we humans understand our environment, then we have all the five senses available to understand what is around us. And actually, among our five senses, then it has been shown, it has been proved that the human use 60% of the brain for vision tasks, right? So the eye vision is very important to understand our world. And that's why I think for the machines to be independent, nice vision systems might be a core technology to push. And if we look at, so yes, on the bottom here, and this figure, the bottom is digital world, and on the top is real world. And what we want are machines that can be intelligent in both digital and real world, right? So the machines have all their understanding on their models, AI models that is running on the digital world. And today we see with ChatGPT and large language models that machines are becoming very intelligent in the digital world, right? I think ChatGPT passed most of the Turing tests, like the intelligence tests. So machines have achieved almost like human intelligence in the digital world, but still for today, in the real world, machines are kind of dumb, right? We still have to drive all the machines and they are maybe not very efficient. So I think we in the lab, but not only us, like I think many other research lab in the world now, they are pushing uh, towards bridging this gap between the digital and real worlds. I think what we need, what kind of research that is now very trendy, is to work toward a large vision model, right? And so that the machines, when they are in the real world, they can bring their intelligence from the digital worlds and directly translate it into real tasks. And yeah, and that can be also interesting for like all kind of metaverse. So I think now Meta, for example, is putting a lot of money, like maybe billions of dollars, into trying to develop these large vision models. And Meta, for example, is investing a lot of money into making kind of digital human, large digital human. I don't know if it will work, but some people have this vision that we can build a huge AI that will take everything from like language models to vision models to animation and VR. I still think like it's good to separate for now everything, but well, that's kind of one direction people are working.
So I have one question. So
Yes.
so I understand what is a chat GPT because I use, but what is a sort of large vision model? So what is the ultimate goal of the large vision model?
The large vision model, so it will be a model that can understand. So you know, from just from 2D images from cameras, there is an ambiguity between what comes from the geometry and what comes from illumination, etc. So a large vision model, now we have some kind of very specific model that if you train with some supervised data, then you can learn to understand a 3D geometry from just 2D images. But if you want to have a large vision model, it means you would like to have AI models that is able to understand the 3D shape and 3D, so the 3D geometry, the animation, and the lightings from, like for example, from 2D images, and that it could do it from in the wild data. And you would like a model that is able to do it for humans and for other objects, etc. So we would like to have large vision models. I think it's models that can be generalized to many different kind of
For example, the
tasks.
so OpenAI have so developed the Sora. So is it a so large vision model?
I uh, I don't know the specifics about these systems, so I cannot answer. I'm sorry. I will look a bit later. I know a bit about what Meta is doing, but OpenAI, yeah, I'm not sure exactly what model is this. So after, I think there are many. It's not very clear, honestly, and that's why I put this for tomorrow tasks. So it's just like what kind of thing we would like, but it's not very clear yet what kind of shape these large vision models would take. For me, I'm very much interested into 3D geometry, right? So I should say, for me, I'm focusing on large 3D vision models, but I'm just saying, if you just interested in making 2D images, you already have many nice vision models that are able to do, for example, object recognition. I think maybe that's what OpenAI. I don't know. I'm not sure about the system you're talking about, but I guess what they're doing is image object recognition, segmentation, and 2D, so 2D image understanding stuff, which is, I think this is already well advanced. And what I was thinking here, and I should have put it maybe more explicitly, is large 3D vision model. It's not just to understand 2D objects, it's really hard to understand like 3D shapes, 3D motions, and generate also 3D shape. I think now AI is good to generate images, good to generate 2D videos, but we are trying in the lab to generate some kind of 3D data, like 3D animations, and it's still very, very complicated. So I like, yeah, like I should have put maybe large 3D vision models here.
Thank you.
Okay, thank you so much for the question. So, yes. Right, so I'm not sure if everybody's familiar with what is computer vision in general. So let me just be briefly summarize a bit what we're trying to do. So I think to go to these large vision models, large 3D vision models, computer vision is a key domain to advance. And the goal of computer vision is to see, right? And to see, it does not mean just to put a camera on the computer, because if you just get an image like this image, we can see in this image that there is a woman, there is a shamisen, there are flowers. We can get some idea that it's a Japanese drawing. But if we give just this image to the computer, then the computer simply sees at first, the only thing it has is just a matrix of numbers. And matrix of numbers that represent like a green, a red, green, blue, like RGB intensities for each pixels. And just by giving this raw matrix of numbers, then the computer does not know anything, right? And so to understand, to actually see what is in these images, like we humans have brain behind the eyes, and for the computer behind the cameras, what we need is computer vision algorithms that basically try to mimic the human brain to see our work, right? To understand and see the world around us, right? And so, yeah, and in my research, I'm actually focusing. So most of the machines are working for us, as I say, and we have kind of many slaves. The machines are kind of slaves for the humans. So for the machines to be more efficient to help us, I think the first step, it's interesting to think about how to represent, how to have a good representation of the humans for the machine. So it means how to build digital humans. And for me, I'm interested into how we can build digital humans. So represent how to represent humans in the machine, in the brain of the machine, by using computer vision. And this is recently a kind of core of my research. And actually, so how to make digital humans is very old topic. It's something that since we have cameras and since we were able to put cameras onto the computer, then researchers have thought about it, have tried to think about how to model the humans on the computer. And the first idea, how to represent a human, is simply to say we can put a 2D bounding box, a square, around the person, and just a label that says this is a person. And that's a decent way to represent the human, actually. And this is actually, this has been researched for a long time. And now this is actually, even if it might feel very simple as a representation for the human, it is very powerful. And it is actually used in many modern technology, in many camera surveillance cameras in the cars now, in autonomous cars to drive into urban scenes. Then we have these kind of technologies that is implemented, that is ready to use. in many systems. So it's very important, and we can have many different kind of fables, and there are still some kind of challenges to solve in there, but I think it's kind of mature technology. And so this is very important, it's good, but I think we can all agree that just a 2D bounding box is not enough to represent humans. We are not just squares. If you don't live in Minecraft, I think we are not just squares. And what is more interesting maybe is to think about the humans as a skeleton, right? So we can think about another way to represent the humans is by using the skeleton, right? Which also, and why is it interesting? Is it because it's because the human skeleton can give information about the human pose, right? So human pose can be defined as a posture or attitude, like kind of combination of muscles to keep stability. Like this guy, he has a very specific pose in the yoga to keep this. But actually, the pose is not just about all the how do you say, all the combination of the muscles, but the human pose gives a lot of information about social stuff, right? It's also a non-verbal way of expression. Like a typical pose give a lot of information about what the person is thinking, what the person is doing. For example, he is thinking. You can also use gestures as a way to communicate, like as a language, actually. And for everyday communication, human pose is a very powerful way to help communicating some information. And yeah, and so this is a very important research domain, computer vision, and we've been working a bit on it. And so in general, this is called the topic is called human pose estimation, so HPE. You find in the literature, if you find HPE, it means human pose estimation. And the goal is to identify in an image, in generally 2D image, the joints coordinates of the human body, right? The joints which are connected with each other with bones, right? And because the human body has many joints, many bones, but for the current systems, it's too difficult to track all the different bones, all different joints. So in general, we use kind of a simplified skeleton, like the one I'm showing here, with maybe something like 20 joints. In general, it's about like the nose, eyes, ears. And for most applications, for the human to understand a bit what the person is doing, it's actually sufficient. I'm not saying that's the only way of representing the skeleton. I'm not saying it's optimal way, but that is what is used most of the time. And it's also getting quite reasonably accurate. And this is also working good on the 2D image. And
Well,
these
I have
can be
one question, sir.
yes.
So is the 70 point of the joint is also standardized or something the different from each method or?
So actually there are quite some differences. So this one I put here is coming from OpenPose, which is maybe one of the most famous 2D pose estimation methods. But actually you can find different ways, different ways of representing the skeleton if you use a different code, a different algorithm. Some the methods are a bit different. Yeah, if you see, for example, even here on this figure, like it's only a little bit different. So this is actually troublesome. Like when we work with the students, we always have is basically you have 2 or 3. In general, you have 2 or 3 definitions of the joints, depending on the research groups. And so we always have to prepare some kind of a translation code that will translate this representation into another representation and vice versa. So it's a bit it's a bit painful for the research. I think there is no agreement on what is the good skeleton. So it's something to keep in mind that it's not it can change, and depending on the data you're using, it can change. Definitely.
Okay, I understand.
Yes. Right. So yeah, so 2D pose estimation is very interesting. And actually now we can even extend this idea of 2D pose estimation to a 3D person. If you put like many sensors, then you can have 3D skeletons. And if you can estimate the 3D human pose, then you can get even better understanding of what the human is doing. And this is very interesting, for example, for sports analysis, if you want to improve performance of athletes. And we are coming close to Olympic Games, right? So maybe we can see some nice 3D capture of the athletes soon. It's also very interesting for robots manipulations. So I think we see recently Microsoft, who established a new research institute in Japan. And so here Microsoft is, for example, investing a lot of money into better understanding human motion in 3 dimensions for this kind of robot manipulations, and in Japan for robots that can assist life in the house. And of course, for self-driving cars, this is also something that is very important. Okay, and I think I have a small video. Yes, so in the lab, so we have a few years back, 2 years ago, we did try to see a bit and play with this 2D pose estimation to see how good it is. And so we tried to apply it for sports and see if we can make this 2D human pose estimation work with a very kind of difficult pose, right? Where the person is doing jumps and completely changing its pose. And if we look, if I can play again, maybe. And actually, the results we got is that it's working quite well. So we had to retrain a bit. We had to prepare a bit our own data set to refine the training of basically open pose. That's like a standard models. But if you put some efforts into preparing some data sets, then what we have observed is that for the 2D pose estimation, current methods now are getting very good. And so now I think the 2D pose estimation is good. So now maybe the current challenges are how to move this to the 3D space, right? But still, okay, so this was very interesting to have the human pose, but still, I think it's not very satisfying. And as a humans, we are interested into having some shapes, right? We're interesting to see the flesh and the shape of the human body is more interesting. This already starts to look more like a human, right? So if you want to have the shape, what you can use, for example, is a template mesh. So that is kind of, I think, what is most used recently. It's a research institute in Germany a few years ago who put a lot of effort into building a very nice template of a human body, which is called Simple Model. And what they did is that they captured some nice 3D scans in the lab. They have a very nice room to make some experiments. And from this many naked body, they extracted some latent space, extracted some key body shapes, for example, and they make a model that where you can play with just a few parameters, then you can play to change the shape and pose of this typical naked human body. And this is used extensively in current researches, for example, to try to make these 3D pose estimations and try to get some information about the human. So yeah, okay, so this is interesting. There are some research here, but I want to jump directly and say that a template mesh are good, but still not enough. And what we really want is to have a detailed geometry, right? Detailed geometry. We want to have the closes and details on the closes. We want to have your own face. You would like to have hair, and you would like also to have a color, so appearance models. And you also want to capture expression, like facial expression with these things. So I think really when we talk about digital humans, we see there is a long history, but with the final goal, I think what we are now working on is to really try to get this detailed geometry of the human body and also appearance and motion here is what we try to do. And so to do it, the first thing we have done is to think about using some hardware, right? So you have some kind of depth cameras and nice GPU computing tools. And with using this hardware, then you can try to capture the word, capture some student information from the word, and then we have worked a lot into how to accumulate, how to build the 3D geometry of the real world by using these scanners. And because these depth cameras also capture video of 3D data, then we can also try to capture dynamic 3D scenes, right? So before I talk a little bit about what we're doing, maybe there is some kind of key techniques I want to very quickly introduce. Yes, maybe I should not spend too much time here. So just quickly to say what was done before, what was existing for a long time, in particular in the robotics community, it's called SLAM, so simultaneous localization and mapping, where you have a sequence of images as input, and on all these images, you detect some key points like the red dots here, and with the key points across different images, and you can match the key points together. And if you can match the key points in different images, then you can estimate the camera pose, and you can do some triangulation. And if you put everything into one system and do some loop, then you can you have some nice systems, which is called so these SLAM systems, and where you can reconstruct some 3D data, right? And this is something that was existing for a long time, and this is still ongoing, and this is still some very interesting research. And this helps to make some kind of virtual applications, AR applications, and this is also embedded into some kind of drones. So this is interesting, but the input is just the color image, right? And for me, like a milestone would be in around 2010. Actually, in the middle of my PhD, I went to do internship in Microsoft Research in Asia, in Beijing. And at the time, the Kinect, Microsoft Xbox Kinect was out. And it was not very successful for a gaming device, but it was super popular for the research. And it was kind of a milestone at that time that we got some real-time, like 30 FPS, 30 frame per second depth sensor and the new GPU. And this gave new kind of possibilities. So now, with using these depth data in addition to the color images, what you can do is that you can build really a dense, right? It's really many points, and you can do it in real time by using the GPU processing. You can make a lot of very simple computations, and this was very exciting at the time. So as many other researchers, we spent many years, a few years, working with this combination of depth camera and GPU to make some nice 3D reconstruction. And one of the first difficulties was how to handle such issues. So with the camera, you have a 2D array of 3D points, so you have to handle a lot of data. And so to make a small scene was easy. How to make a big building, for example, was very difficult. So we worked on this a little bit. Yes, but I'm going. I'm skipping a bit this because I want to talk more about dynamic scenes, which are more close to human. So one aspect was how to go to large scale scenes. One of the problem was how to handle the dynamic scenes, right? Because another very interesting effect of these Kinect cameras is that you can capture video, right? You can capture video of 3D data. And then if you can capture videos, then we can start to capture some motions. And so we had some projects to combine different cameras and trying to capture some animations from these.
I think so. This is very interesting to movie. So how many cameras are you used for reconstructing?
So here there are 4 cameras. I think each camera has a different, or maybe 3 cameras. 3 cameras, sorry, like which camera has a different color. We used at that time, it was a PhD student in Keio University from Simeritz. He was working with PhD student at Saito Lab, and he had implemented a very nice system where he combined, yes, I think 3 or 4 Kinect 2 cameras. And what was interesting, so if you use multiple cameras, then you can have a bigger coverage to reconstruct bigger scenes. And what what's also interesting is that if you use unsynchronized depth data, then even if one camera is 30 frames per second, but if you use multiple cameras, then you can actually increase your frame rate. So we were trying to capture larger scale scenes, and we were also trying to capture more high speed, smaller, higher resolution in terms of time frames. So it was very, very interesting, but it required some kind of heavy engineering, heavy programming. So Sim Merits did a nice work to calibrate all the cameras and synchronize everything on the server.
Thank you.
But this is very interesting. Still, there is still one problem that appears in this research is that you can see that we have actually the depth data is not really a 3D data, right? You only have the data that is in front of you. There are many parts that are occluded. So from this viewpoint, everything seems good. But if we turn 90 degrees, you will see that the human body, for example, this guy on the right does not have, is missing a leg, right? So that's why many times depth data is called 2.5D data, right? So the problem is from this, if you just do reconstruction frame by frame, here it's one depth image, one mesh, basically. The goal was to make this meshing very fast. But here you can see some data are missing, right? So this was kind of one limitation. So now the next topic was, okay, so since we are able to, if we were able to track the cameras, like what was done in SLAM, is that you can accumulate the multi-view data to make a full, what we want to do is to have a full reconstruction, right? Is to capture the data of the observation and then output one full 3D model of the human or the map you want to create, right? So that can be used later or seen from many different viewpoints. And so one project later was to say, okay, we know a bit how the human body is moving. So let's try to build only from one camera now, only from one LGBT cameras, how can we build a full 3D shape, full 3D model of the face, for example. So not just for the head, right? But the person is moving in front of the camera, it's talking 3D, and the goal is to accumulate all the depth data into one common 3D model of the face, right? And what we did is to combine. We know, so if you look at the template representation, template meshes of the human body, then we have some main informations about how the human is moving. And in particular for the face, we have some nice animation models of the human body. So the idea was to combine these template data about human motion with some kind of deviations, of some kind of augmenting these kind of templates with observed data, right? And to explain quickly what we did, maybe I should introduce very briefly what are the plane shapes. And so the plane shapes are basically key shapes, right? Key shapes of the human. So now I explain this in the context of the human face, right? So for the face, the plane shapes will be some key expressions. Okay, so you have a template and you have some key expression of the face, like one left eye closing, mouth opening, and etc. And these key shapes, in general, they are prepared by some artists, like computer graphics artists. And if you have these kind of key shapes, then now you see, if you try to optimize the 3D position of all the vertices of this template mesh, it's very difficult. But if you have these blend shapes, you can make the problem much simpler by just trying to optimize some weights for each of these key shapes. And then when you have the weights for each of these key shapes, you can just blend, you can mix all the key shapes together to make any kind of new expression. Any kind of new expression that would belong to the space defined by these plane shapes, right? And if you have these weights, you can also use these weights to animate another model, right? So that was kind of a funny applications we did with Onizuka-ko a few years ago. And for example, Onizuka-ko is moving in front of the Kinect camera, right? and every time it's moving, we are optimizing these blend shape weights. And you can see that once you have a blend shaped weight, if you prepared some kind of blend shapes for different kind of characters, then by simply moving in front of the camera, we can do what is called retargeting, right? We can retarget the expression onto a virtual character. So this is basically the key tool for what is called blend shapes. And we have these nice tools from the computer graphics, community. And the idea was to combine these blend shape representations with depth data to add. So these blend shapes allows to make, instead of tracking the camera here, what we are trying is to track the human face motion. And now the human is not moving rigidly. The human is doing some non-rigid motion and with the face doing some deformations. And the idea is to use the blend shape representation to do some non-rigid tracking of the human expression. And if you can track this non-rigid expression, then you know how to deform your input depth data into some kind of canonical representations. And here, as a canonical representation, as I would say, canonical representation means kind of reference space. And then you can map your depth information or 3D information into this canonical representation, so like a rest pose, and use this to do some personalized 3D shape reconstruction. And yes, so this is just and this is how it works. So here are like the template blend shapes, for example, that we used. And here would be the same blend shapes where you have added, you have put your geometric knowledge on top of it. And I hope I have. And here are some results, right? So basically, maybe I can show again. This is okay. So this is a key idea, right? So again, you have this template motion template model for the motion of the human face. And on top of it, if you can build this green and red image here, kind of represent like a 3D information, right? If you can build it, then you can have personalized plane shapes. And the idea now was to use the Kinect depth camera, and in real time, as the person is moving in front of the camera, then you're tracking the motion of the person. And these 3D geometry here, if you look, it's getting updated at every frame. And every time it's getting updated, then your 3D model is being refined and optimized. Okay, and the more it's optimized, the better the tracking becomes, and then you're going into kind of a good cycle.
So I have a question. So how about to reconstructing the eye? This is a so white eye.
So the eye or white. So this was to be future work 5 years ago, how to put the eye and also how to put the tongue and the teeth, which were not in the model, which were not into this template model. So there are some research which like put some eyeball and to do the eye tracking to simulate the eyes. So this was to be future work at that time, but we did not totally finish it actually, because what came after this is boom, is AI.
Okay.
AI stuff came and deep learning came, and then we shifted a bit. But this is very interesting, and this was the last the last comments we got on the last paper from the reviewers was, oh, you should add teeth, tongue, and eye to the to the model. And we say, yes, we will do in the future works. And still, actually, we had nobody to actually finish this. That's a good question. I think now today maybe you can find some models with the eyes. Yes. So this was very promising, but very interesting. And there is, so this is basically here was just to sell the concept, right? The concept about how to make this reconstruction with LGBT data, how to make a final product. Yes, this would be for the for the company to do. I think just adding the eyes and the mouth also. We were not sure if it will be enough to get next paper, basically. And at that time, actually, after this paper, there was kind of a revolution in the field, which was deep learning. And now many people shift from using hardware to using AI solutions to make these 3D reconstructions. And so with AI and deep learning, now we are kind of revisiting all the standard, all the well-known topics, because with deep learning, actually, problems that are inputs, so problems that normally are not, cannot be fully solved, like problems that have many solutions. For example, how to reconstruct geometry, how to get shape, color, lighting from just one single image. This is impossible because there are many different. If you just look at this image on the right, the 2D image, there are many kind of combinations of shape, color, light, viewpoints that would make the exact same 2D image, right? So this doing the reverse problem is an ill-posed problem. There is not one solution. There are many solutions. And so for a long term, this was supposed to be impossible, right? But with deep learning, it's still ill-posed problem, right? There is not one solution, but with the deep learning, actually, AI can output one of these solution. And in general, if we train with some data, it can output the solution that the human will feel the best solution, right? The one which is smoother, for example, or the one that resembles some data. So this is very interesting that there are actually, with using AI, there are now new solutions to work with. And so following the trend, we start to see, okay, so now we were using hardware, we're using the Kinect camera to reconstruct the human body. So can we use AI now to do this, to extract the 3D shape of the human body, but without using the depth information, just from one 2D image? And again, this is something that is supposed that is ill-posed. There are too many ambiguities to solve the problem. But as I said before, we have a lot of knowledge about 3D human bodies. And in particular, we have many template models for the human body. And the idea is that if we constrain the neural network with information about the human model, then actually we can train the neural network, a deep neural network, to transform an input 2D image into a 3D model of this person. And yeah, and this is still a very hot topic in the computer vision. And I think every 3 months or every 4 months, you can find dozens of new papers about these topics. So it's very interesting. And so here, for example, is what kind of results we can get. So if you have this kind of input image and you train with data which are this kind of quality, then you can train a deep neural network to output a mesh like in the middle, right? Which is getting very close to the ground truth. So these 3D meshes are directly the output of a deep neural network that transforms the image on the left to a 3D data on the right. Right, so this is things we can do with AI and estimate 3D shape of a human body just from one image. So just to go, I won't go into the detail because it will require a lot of time, but just very briefly to explain a bit what is behind this network, let me just introduce one concept which is called sign distance function. So it's an implicit way of representing the 3D shape, the 3D geometry, right? Here I make the illustration in the 2 dimension, but for example, the explicit shape here will be these curves, right? And you will have, for example, some vertex on these shapes, which will be connected with edges, right? That would be an explicit way of representing the geometry. That's what is called a mesh. That's what is used in most of computer graphics software, right? Now, what you can do actually is to define a function in the space, which is called like a sign distance function, where each point in the space takes the distance to the surface. Okay. And if you are outside the surface, then you can say the distance is positive. If you're inside, then you can say the distance is negative. So it becomes red, right? So it's negative in the red part, it's positive on the blue part. And when you come close to the surface, when you are on the surface, distance becomes 0. And what you can see now is that with such kind of function, this function is defined on the whole 2D space, right? Or if you're in 3D, it will be defined on the whole 3D space. But what you can say is that the surface are all the points in the space so that the SDF equals 0. Okay, it's the 0 level set, it's called. So this is one way to extract the explicit surface with this kind of function. If we discretize, okay, we are on the computer, so we work with in discretized space. So if you discretize a space with a grid and record the SDF values at each pixel or each point, in 3D it will be called a voxel, each point in this grid, then you can see that the part where the sign of this SDF is changing is the part where it's changing, then you can extract where is the actual shape that you want to reconstruct. And this is an implicit way of representing the 3D shape. And it's super interesting because now, instead of trying to find out where are the vertices, which vertex are connected to each other, how many vertex I have to represent my shape, then you can cast the problem of optimizing this 3D surface as a problem of optimizing the SDF values in a finite grid, in a grid that does not change. The grid itself does not change. Only the values of the SDF function change. And if you change the value of the SDF, you can actually represent any kind of shape in this space, which is super interesting. And the second point, it is also very good for deep learning, right? Deep learning is very good to do some kind of convolution tasks and to predict values into a predefined range, right? If you want to find predict the value of each of these points, this is very easy to write with deep learning tools, right? So that's the key idea to train. Basically, what we want to do is to train an algorithm that takes as input to the image and learns to output the SDF values on a predefined grid. Okay, that's the key idea into most of this shape to 3D reconstruction. And so, yes, and then, of course, that's the basic idea is just to do on the uniform grid. And of course, there are many challenges to actually make it work. So for example, if we want to make the whole body, then the grid becomes too big and it does not fit the GPU. And so what we proposed in this work is to use a human prior, like to have a human template, and to say we don't need to estimate the SDF values at this corner here. We know the human body should be around here in the middle, so we just have to predict the points around the human shape. So we can restrict the space to predict the SDF only around the human body. And then it means this reconstructing the full body shape with high accuracy now becomes doable. It fits into GPU, right? And so if you have some ground truth data, then you can transform your 3D scan into implicit SDF representation, and then you can learn. If you have a neural network, you take an input image, you transform this input image into a feature, and you decode your feature into SDF fields, and then you compare your output SDF field with the one that comes from the ground truth 3D model. And now you can optimize the parameters of your deep neural network to directly output this SDF, right? So during the training, we use this ground truth model to supervise the training of the neural networks, but during inference, then you can hide this. you can only take as input the color image. Right. So this was very cool, very interesting. Kind of, we could build some kind of prototype to do it. But obviously, like the problem is that we have to prepare these ground truth models to supervised. That's what come like when at the beginning about the question, what is large language vision models? That's what kind of things I have in mind, is that current models, they are kind of restricted to this data set that is used to supervise the training. And preparing 2D images is easy. Preparing 3D scans with high quality is very difficult. Even today, like a high quality ground truth 3D models is very difficult to capture. So we don't have enough data to actually train a network to reconstruct anybody, right? Basically, you can only reconstruct guys which are close to the ground truth data sets. But we can make them in different pods, which is already very interesting. But we are kind of limited to the data sets. So, okay, that's also kind of limitation, but then, okay, then if from one view still there is some kind of limitation, another research still is to do, we can use multiple images. And if we use multiple images to make the 3D shape, then it's called multi-view 3D reconstruction. And it's actually a research term that is here for a long time. And this is a research topic that is now being revisited. Okay, let me speed up. It is being revisited with AI, right? So yes, the idea is if you have several images, the idea is to first calibrate. Okay, so put all the, if you know the position of all the cameras, then you can do some 3D triangulation to reconstruct the shape. And once you have the shape, you can reproject into the input image to make also the arguments, right? So this is kind of the standard pipeline to make multi-view 3D reconstructions. And today, what is very trendy is the big trend is to recast, reformulate these multi-view reconstruction by using neural resonance fields, also called nerves, right? And to reformulate the 2D image formation as volumetric renderings by integrating color along lines in the pixels. And what's interesting is that you can formulate the color at the pixel as a differentiable integration of colors and geometry along the line of sight. And then this means that if you have multiple images, then all your pixels are done in kind of the neural networks makes everything differentiable, and then you can easily optimize. You just give your rendering formula, multiple view images, and then you just ask the network to optimize its parameters so that everything becomes consistent. And it's working very well. So it's a very interesting topic now. And okay, so I think I'm almost running out of time. So and now what I will just make me go a bit quickly to explain what we are actually working on today. So it's still work that is in progress. So I have, maybe it's not full results, but so based on this, what we are working on today is instead of trying to optimize the values at the grid, what we're working on is can we change the grid? Can we change the grid to make a better reconstruction? So what we are doing, for example, if you have like multiple view images like this, the goal is to reconstruct the 3D model of the object that is seen in the images. And what we're working on is to, instead of updating only a celestial value, is to think how to discretize the 3D space so that the optimized, obtained SDF field becomes more and more precise, but while also keeping optimal use of the space, right? And these are kind of results, kind of research we're doing. And here, the idea is that although most of the current research are using uniform grids, right? As I showed before, actually uniform grid is not the optimal way of discretizing the 3D space. And we have nice tools from mathematics and a nice tool which is called Voronoi diagram and centroidal Voronoi tessellations. Actually, that is should be the best approach. So we are working on this now. Also, with Jane from Stanford, we are working also into new custom differentiable rendering technique, not just a volumetric, but instead of doing volume, which can be also kind of long to optimize, we are also working on to doing the triangle explicit surface rendering and try to find like a custom differentiable way so that we can optimize the 3D geometry from 2D images. And then if you can obtain some kind of nice reconstruction like this. Yes, so other topics are related to, so we are interested not just to make static humans, we are also interested to make some animations. And so, okay, so as we saw before, like there are many techniques that allow us to make some 3D model of the human body, but they are static, not dynamic. You have some method that exists to you put a video and then you can reconstruct a dynamic human, like a bit like I showed with the face. This is very good, but then you can only replay basically the video in 3D. So there is no, it's not controllable. And here one research, what we're interested in is to train a neural network from a given motion or given images to reconstruct these animations. And what we want is to have animatable avatars, right? So basically you capture some 3D data, you have the human pose, and you train a deep neural network to generate new full 3D human pose, right? With close wrinkles and everything. And you train the network to transform a sequence of human pose into a sequence of 3D meshes. And the idea is that when you have trained this, then you can control your avatar by changing the input pose. So basically you train with some motion sequence, and after you can play, put another human motion, and it will create another mesh in different pose. And this is, for example, this is in green, it's the training. So this is data we have, the observed data, right? So if it's play again, right, you have as input human skeleton pose and also the 3D scan that correspond to the pose. And we feed these data to a neural network. And then the neural network, when it's trained, then you can put totally different human pose that the guy is dancing. And on the top right, then the network outputs the 3D mesh that correspond to this new pose, right? And with using some regularization, what is interesting is that it's not just a template, so you can see some wrinkles in the poses, and the wrinkles are not just linearly transforming, but are having some kind of natural deformations. So this is also, it's called animatable avatars. And moving the last topic, just 2 minutes, it's about generative AI. We also have generative AI for 3D. And the topic here on this research is how to generate gestures, not from the human pose, not from the images, but from text. Okay, so if we want to have robots that can communicate with humans, it's important that the robot can talk with the robot. So we would like the robots to generate new human poses from text. And here, one key part of the research is that we separated the text into like the text that correspond to beats gestures, so just like rhythm in kind of the gesture, and text that correspond to imagistic gestures. So part of the text that has meaning, like if you say, I want to make a donut, and then you make the shape of the donut with the hand to explain what you want to do, right? And if we can disentangle, if you can separate the words into what kind of gesture to generate, then we can train the network, the robots to, yeah. Can you listen? Do you have a sound or not? Yes?
Mm.
Okay. So, Yeah, so the goal line, you see there is the sentence on the bottom, and the goal is to make this human avatar to move as much realistically, naturally as possible by learning from this observation data. So it's still, yeah, so it's still not clear, but instead of doing just random motion, we can have more natural motion, basically. They can tell that the robot, for example, has some kind of beat gestures. Okay, and this is just to finish that Teshima Cohen PhD student in the lab played and tried to, we have this kind of robot from Microsoft, which is a DIY, do it by yourself robot, and then you can actually program a real robot to move, to make some kind of gestures. Yes, okay. All right, I belong. So yeah, so just to finish, this is my last slide. So going back again, from going from digital world to real world, we are now trying to make some kind of bridge between the cyber and physical worlds. And if we are, I think for the future, we are searching for better, smarter vision models, like 3D vision models. So I'm thinking about large 3D vision models to better understand our world in the 3D dimension. And this has many applications for in communication for autonomous vehicles and for the medical systems, to all these to better understand our world, to better, and if you are thinking about digital humans, to better understand humans also. All right, so this is my last slide. As a summary, I think today's we depend totally on machines, so it's allowed us to become very rich, but it's also a bit scary. And I think we need to think about the smarter AI, smarter machines for our future, because petrol and energy will not be here forever. So what happens when we have no machines is, or maybe we need to think a bit more. And so in my research on the computer vision, we are moving towards trying to build such kind of large 3D vision models and trying to reconstruct, understand our world and understand humans by using AI. And I think that is one way to bridge the gap between digital worlds and real world. And if we can do it, then maybe machine can be much more helpful for our everyday tasks. All right, that's all for me. Thank you very much. I'm sorry I've been a bit long.
Yeah, thank you very much. So is there any question from the audience? No cases I questions or something. So yeah, I have some question about the AI part.